All right. It works. Cool. All right. Yeah. So, all right. Today, like I kind of, we kind of missed yesterday, right? Or I guess we didn't have our study group yesterday like we normally would. But it's kind of works out pretty well because since this is going to be section, ooh, I forget the numbers now. Is it 28 and 29 was logistic regression? And then I think 29 was more logistic regression. It kind of works out really well. We'll kind of combine them together. So, let's see here. I'm going to pull up, let's see here. I made a new, oh yeah, by the way, if you go to the repo now, I try to make this a little bit easier to navigate. The README now has like the different modules and stuff like that. So they're a little bit easier to see what section, because they're kind of a little bit of crossover. Plus I know sometimes we'll kind of rearrange the curriculum a little bit. So this will hopefully make it a little bit easier to kind of go through. And notice in-depth logistic regression, I just put it all on this introduction part. So we are first going to talk about, not evaluation metrics yet. We're going to talk about logistic regression. So where is that one located? You are, pull it up. There, machine learning, okay. So I put under machine learning. I think that makes more sense in my thought process. So we'll see our intro. Oh, good. And I think I made this nice and easy for future Victor to go through. So kind of introducing to logistic regression. This is where like I know you guys had some questions talking to. So if there's questions that kind of come up or you want me to go into more detail, just feel free to interrupt me, you know, and kind of go from there. But basic idea for logistic regression is that we're basically going from linear regression and using the tools of linear regression to make something that's more classification. So if you remember like linear regression, we're really trying to find a relationship. And so you think of like what we're doing, basically inputting a whole bunch of variables, our features, right? And then outputs our target, right? What we really care about. So if you remember back in like our housing project one, we had all the different features of like a house or like an area or whatnot, and then trying to predict the price, which was our target. So that relationship is like regression, meaning in the sense that we can have multiple, what's it called? Like a continuum of possibilities. That's not always the best thing for every model. Sometimes we just want to know, is it basically like a classification? Is it, you know, is it green, yellow, or blue? Like that doesn't really make sense to have a spectrum. So if you think about it, we didn't really talk about like how to make a prediction with a linear regression model on like on something that's categorical on a target. And that's because we really can't. So that's where logistic regression kind of comes in for classification. And classification is kind of a very, you know, common machine learning application. And so usually the idea is like, you know, for example, image detection. Like this is going way beyond like this logistic, but like if you imagine image detection, it's like, oh, is it a dog? Is it a cat? Is it a person? You know, is it person A? Is it person B? You know, all those different things. It's basically a yes or no question. So classification kind of goes with a yes or no. Now I kind of put this little note here, so like you're either with us or against us. It's kind of because like in classification, you think about it, it's like, oh, it's either a yes or a no question, but how do you deal with three types of, you know, categories, right? If you're like, yes, well, let's say like green, blue, and yellow. It's like, well, it's not really, if it's green, it's not blue or yellow. So basically classification, the way it works is like, there's either a positive, which is like, let's say green, and then everything else that's not green is going to be a negative. So that's kind of the idea, is where you either have it predicted as one category, or it's either this category or not that category. So blue and yellow would, for example, be no. So that's kind of the way we kind of get around the idea that it's only a yes or no binary answer. Okay, does that make sense? Cool. I see some nods. Cool. So if we go back to like linear regression, and it's going to look very familiar from like the curriculum, you remember that it looks something along this way. I also like that beta is kind of closer to like, if you notice, we're moving further and further away from like the classical y equals mx plus b. And that's because we're trying to make it more generalized, because as we get into more algorithms, it'll make more sense to use these different like coefficients and different, you know, kind of terms, versus using m's not going to mean as much in other algorithms. So just know that basically it's a line, right? It's a hyperdimensional quote unquote line. So it would be hyperplane technically, but we've seen this before. So classification uses logistics. So logistics basically is the idea that we're taking the probability of being in a particular group. So what we can do, we can take what we already know, linear regression. Remember, like linear regression is kind of like a well-studied thing. It's very powerful. It's basically the only real classification tool that we've used, maybe besides naive Bayes, but like it's really the only thing we use to like model stuff, right? And so now we can take this well-known thing and transform it. So instead of transforming to say, oh, what's the value of this output, we say, what's the probability of this output? So what's really nice about this guy it's basically saying we take our linear regression here and essentially we're transforming it so we have this nice, beautiful little equation here. And what's kind of cool, if you know like the kind of the mathematics, right? We just basically have this multiplied e to the negative beta 0, e times negative beta 1 times x1, and so on. And one thing here, I don't know if I actually put this in here. Okay, good. So I think you guys already know this a little bit, but if you put in these numbers, basically there's only two outputs you can have. Or sorry, your range only goes between two integers, between 0 and 1. You'll never get less than 0, you'll never get more than 1. You always go in between those two parts, which makes it really nice kind of like to, for probability and everything. Okay, cool. Any questions on like how we go from like linear regression to logistic regression, at least mathematically? Okay, cool. All right, yeah, and just know that our job now is just basically figuring out this beta 0, beta 1 in this exponential. You can also view this. So what this graph will look like, so this will be kind of nice when we talk about actually classification, but what this graph looks like looks something like this curve, like this, where basically the top one right here, that it's hyperbolic, right? Not hyperbolic, asymptotic, right? It's asymptote, right? So it approaches closer and closer to the value 1, and then this would get closer and closer as we go into a negative infinity, would get closer to 0, right? So basically, if you get very, very low values over here, or very, very negative values, you would get 0. If you get very high values over here, you get 1. And it's going to be shifted off right here. And right here, at this point right here, is 0.5. So you can kind of see like that's kind of the inflection point going on here. And so that's what it looks like if we were to kind of graph this guy out, if we set this y equals to here. Another way you can kind of view this is that we're actually doing essentially, I won't go through the mathematics, but essentially what we're doing, we're also doing a linear line or a linear regression, but instead of transforming, let's see here, this is like our y value, this is our x value. Essentially, we're doing something like, I'm not going to go through the full mathematics, but what we call our logit. So basically like the log transforms of these variables. So you can think of them either way, generally we'll kind of talk about it in this form, but know if you ever see kind of like the logits like plotted in a line like this, it's explaining the same thing. It's just a different way of looking at it. Cool. All right. So I gotta get back my mouse. There we go. All right. So let's go ahead and try looking at how to implement this stuff. Okay. So let's see here. I want to see if I want to go into here. All right. So yeah, we're going to go into about implementing it, and then I'll kind of explain what's going on here, right? So this is going to be very similar to like the curriculum's data implementation, like in the coding lab. Okay. And note that I'll use sklearn, just because I use sklearn for a lot of different things besides just logistic and linear. I think that I actually don't know. Does the lab do stats models, or does it use sklearn, or does it do both?
I think it has a start in stats models and then go to sklearn. Does that sound right, Andy?
Yeah, it's mostly sklearn.
Okay, cool. And that makes sense because we'll use a lot of the metric tools from sklearn for not just logistic regression, but other classification models. Okay, so we're just importing our basic stuff. We're actually going to use some data that's already put in here. You'll see me use iris a lot. So the iris data set is pretty typical. I think it's like about 150, I think, data points. If you're curious, it's basically about like flowers. So there's different features on the flowers and what type of flowers there are. So this works really well for our basic, did I already run this? Oh, let me go ahead and do a kernel clear out so we don't get confused. So I was confused, like, did I already run it or not? I've been noticing it takes a while. Oh well. But we'll do a quick display of this stuff. My Jupyter notebook's been weird stuff. I gotta check out the environment. So let's go ahead and stop this guy. Restart. I'm sure you guys have gotten to these things before, right? Yeah, fun stuff. Okay, let's go ahead and run this guy again. Oh, I know what's going on. Okay. Okay, I tried clearing out the output for some reason. You can see like it's not clearing it out. So let me go ahead and just close a halt. And let's try this again. If it doesn't work, shut it down. Okay, so you see it's not running anymore. So hopefully now, before I run it, I'll go ahead and clear out the output so we don't get confused. Come on, go away. Okay, well, while this is kind of clearing out, it's taken a while before, but I'm basically just manually putting in this data frame. So we have a nice usable data frame going through. Note that the targets will have 3 different targets. There it goes. So let's go ahead. So run all above. Okay, so you can see here our different features: sepal length, width, petal length, width, and then our target's going to be what class it is. There's 150 points in here. This doesn't really tell us much, but you can see the standard deviation. Yeah, it's not, it doesn't really help us say the distribution of the class, but I think it's relatively well distributed. And you can see basically our different features here, okay? And of course we have 0, 1, 2. So we're gonna only treat it as like either this class or not, just to make it simple. So it's gonna be a true, false, like a binary coding versus like 0, 1, or 2, just to make it a little bit easier for us to kind of introduce it to. All right, so we'll go ahead and let's see here. So I do a little plot here. We go ahead and explore some graphs to show that doesn't make sense to do linear regression. Yeah, so if I try to go ahead and graph this out, we'll see basically, you know, these points are more or less essentially classified altogether. I could try to write like a linear regression through here, but it wouldn't make sense to go 0, 1, 2, especially you see this petal width right here. These are really all close together versus like me be able to predict across it. So I could technically try to do linear regression here, but I'll get values that are like, oh, like with this petal length, with this, you know, petal length and this petal width, I might have something like 1.2, which doesn't really make sense for the class, right? So this is where I say, oh, this is really a classification problem. So now we go ahead and just prep the data for some classification. So note that I'm just basically going to get the target. So basically everything, get the features and then the target. I'm going to normalize it. So note that we tend to normalize. It technically would work without normalization, but it will perform better. And plus most algorithms will require that you normalize, basically. Those values are relatively small. If the values are too large, it basically overpowers the algorithm, okay? And I'll do my X-train S-test split, right? Sorry, your test train split. So I got my split right here. Know that just put a random state so we can just keep it consistent. And here we go. So create the logistic model. So note that I'm just going to model, note the C parameter. I just kind of put that in there just to make it consistent. I think this is very similar to the curriculums itself. But this C parameter is basically related to regularization. So we're just kind of making that pretty high right here. So which means low regularization, wait, it's inverse. So it's low regularization, okay? So we're just not considering that. And then all I have to do is the X train fit. Cool. And this basically, this model.log, this is just telling me the parameters of this model, but doesn't tell me anything like what's happening, like what's going on here, okay? And note that in the, oh yeah, go ahead.
Why, so is there a reason why you would specify one solver over another? Like I've been specifying liblinear, but why, yeah, why that one?
Yeah, this is, to be honest, I think I mostly copied this from the curriculum. That's probably why I ended up using it so it's consistent. But the solver just really is about, what's it called? Just the way it performs the gradient descent, essentially. So some might perform differently than others. For the most part, at least in my practice, is that like I haven't had to like deal with the solver too much. Usually I'll just use the default on there and just go with it. Because usually, to be honest, is that I'll usually use logistic regression just to see how well it performs. Say, cool, do that one time and then move on to a more advanced model. But I'm sure there's more details, like I'm sure, like say like why you would use one solver over the other. But,
Cool. Thanks.
No problem. So yeah, so just know we got a fit, and there's some in the background here in this dot fit. We're really doing gradient descent in the background. So, or at least some other fitting method, usually gradient descent. I think sklearn uses that by default. And then we have here, it's like, okay, cool. We have our model trained, right? And now we can check out our test, right? And see how well it performs, right? So I have our now predictions from xtrain and xtest. So hopefully this right here should be pretty close, right? So since we trained it off that data, we should hope a higher percent. Our test data, would we expect that to be, what do we expect it to be higher, lower, or the same as this training prediction? Like at least the accuracy.
It'll probably be less accurate because it hasn't been trained on it.
Exactly, right? So that's almost universally true. In fact, if you ever get to the point where like your test data performs better, it's almost like you might want to like squint your eyes like that's some random chance, or something else happened where, for example, there are things, for example, leakage, where you don't do this train split ahead of time and you accidentally train it on this data. That can happen too. Or what can happen as well, this is actually, to be quite honest, this is not perfectly kosher. You would normally in production environment, what you would do is you would do your train test split, normalize based on the train data, and then use basically your normalization, which will be a pipeline to say, all right, now normalize it to the testing, the training data. And so that way, because what happened, so anyone got an idea like why you would do the normalization just on the training and not for all of it together? What is normalization going on? Like, what does it do?
Well, then wouldn't you be messing with like the test, like, because if you had certain, I guess, values that are different from test and train, the values from the test would affect the normalization, and then when you go to run it, it would already be affected, and it would have already seen the test values.
Exactly. Yeah. And that's what we want to avoid. We don't want it to know anything about the testing data. Like it should like be completely oblivious when it trains it. The problem is when we normalize it, considering all the values, it's going to take the maximum, the minimum, and it's going to try to basically make it into a unit vector. The problem is like, well, if it knows the maximum, then it technically has seen the data to decide what that maximum is. It might seem a very subtle and like kind of like, oh, it doesn't seem like that important. But the biggest thing about like pretty much all like machine learning is like, be careful with your data. The data you feed into it is going to be one of the most important parts of like, you know, how well your model performs. And there's interesting leakage examples like that have happened, and they're like, whoa, like did not expect that happening. Kind of, yeah. I can, if you guys would like to, you can ask me more about that, but we'll touch that more again. But just want to keep that in mind that technically it's not kosher, but it's just kind of getting that idea how this works.
I have a quick question.
Oh yeah. Yeah, you go.
Okay. Okay. Mine was over the train test split. I was reading something earlier that I guess it talked about a parameter that maybe wasn't mentioned in like our classes and stuff, but it talks about a stratify in the train test split, and it was saying, you know, like if like kind of like for a binary classifier, if you have like 10% yes and 90% no, then you should stratify it, I guess, so that whenever like your train and test are split up, so you have like 90% no and 10% yes. Do we need to do that ever, or is that kind of like?
Yeah, so that's a big concern. So like one is that when we do the train and the test, you assume that okay, so oh man, there's so many parts I'm trying to like make sure I get while we introduce it to, but I think it's an important example. In reality, there really isn't just two sets. There isn't just the train and the test set when you actually do this in deployment. There's really, in a sense, there's the training set, there's a test set that you never see until the very end. And there's actually between these 2 points is a validation or a dev test. And that's the thing where basically we're using our test set. Essentially, as you get more and more model, like, or you try to train the better model, right? So you might have multiple ways of doing this. You'd use the same train data, but you don't want to keep testing each model against the test set, because essentially you're going to choose the model that does best on the test. But then the problem is like, well, then now you're kind of fitting to the test indirectly, right? So really what you want is an intermediary where it's like, okay, let me just go ahead and train these parts, compare it to the validation or dev test, depending who you talk to. That's how they call it. I'll call it validation usually, but your validation, say, you know, how well does it perform on validation? And then once you're done with all the models, you're like, okay, this is the one that performs well. I've checked it overfitting. I've done a few iterations kind of going through it. Then you would test against your test set that you've never seen before. And your test set really is kind of like emulating data that you haven't seen. So like in production, you will get data that you have never seen, and you want to make sure it performs well on that data. So that's kind of like what we're emulating in a lot of ways. So that's one thing to consider. I just want to make that clear. But when you're doing like where you're saying like the stratified example, you want to make sure that your, what's it called? Your train and your dev come from similar populations. You don't want basically to have it where all your train, for example, is let's say it's like 5% is like no, and like 95% is yes. Well, if your training data basically gets a higher percentage, because out of pure chance, right? It gets mostly all yeses, right? So like 99% of them is all yeses because there's such a few number of no's. Well, then your training data is going to say, hey, I'll just name everything, you know, like yes, for example. This is a very simple, like simplistic reason, but there's other things that you can do too that could mess it up. But I could say all these are yes, 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 yes. Then when it goes to the real population, which there are like, you know, a certain percent, let's say 5% are like no, it's just going to assume that, and it's going to look different than your trained validation. So you always want to make sure that basically your train has a similar distribution, and that's where stratified sampling might make more sense, where like, hey, let me make sure that I get a higher proportion of this. In some algorithms, it might actually make sense to even like upsample, which we'll talk about. I guess we talked about a little bit last time, like last module, where we talked about upsampling or downsampling. Is that right? I think we talked about that, like section 24. Okay, like resampling. And the reason why you might upsample is because like, hey, like maybe the model, like you want the model to really figure out how to identify yes. So a classic example of this, like for self-driving cars, is you want to avoid accidents. Well, let's say, for example, someone jumping or tripping in front of like the car, right? Or jumping in front of a car or something like that. You want to avoid that. Well, those instances from your training data probably are very, very rare, but it's something you want to train for, right? So what you might, even though it's like only like, you know, 0.001% of the time of ever driving, you know, like that ever happens, you might inflate that and say, okay, let me upsample it so it becomes more prevalent. And that way you can train against it and identify those things. Otherwise, the model's going to say, hey, I don't really see this too much happen. I'm just going to ignore it, which is what you don't want, right? You're essentially, by upsampling, you're increasing the importance of like how it is. So there's different methods on how to do this, and it depends on the algorithm too, of like how it goes. Does that kind of answer like a little bit what you're asking, Andy?
Yeah, I mean, no, like that.
Okay. Mm-hmm.
I guess like just when like would it be useful for something like this, like to see the Y values first and be like, okay, like they're pretty evenly distributed zeros and ones, don't worry about it. But if it's like 10%, 90%, maybe stratify it so that your train and test are similar.
Yeah, it's one of those things. So technically, if you random sample, it should, in average, get about the same percentage wise, which in this case won't matter too much with logistic regression. However, if you had something like a 10%, it might actually make more sense even to upsample it. So you might not even want to say, oh, let me just get 10%, a 10-90 split of like yes and no. So you might say, oh, I want to get closer to 50%. That way it really learns what a yes is and what a no is. And that's kind of like the way you can do that. If it's a relatively like, let's say like 40-60, those could even be fine in the sense of just randomly sampling, or you could stratified sample to make sure, or I should say stratified sample. If you randomly sample, it gets a similar distribution. But if you stratified, you can essentially say, okay, let me go ahead and pick 50 from the yeses, 50 from nos, and that will be a 50-50 split. That way it kind of has equal importance. And this is essentially upsampling. One technique I'll kind of throw out there we haven't really talked about is SMOTE. I actually can't even remember what it stands for, but basically it's a way to upsample more values to kind of get essentially fake yeses or something like that, where you need more of those parts. But yes, you would definitely want to check out the population, which I kind of skipped over, which I kind of like said very quickly. I said like, you know, going off of, what was it here? I was kind of quickly looking at the target. If I was being more careful, I would say, what's the classification? How many are going into yes and no and stuff? So yeah, I should say distribution of the target is important. So like what class it is. Cool. Okay, good questions. And then I know, does that answer everything you needed, Andy?
Yeah, no, I'm good. I mean, I know
Okay,
a lot
cool.
of stuff's just kind of like case by case, but we can keep going.
Yeah, and we'll go back to it too. So like as those kind of come up, definitely keep asking those questions and we'll revisit them. Cool. And then Jenny, I know you had a question too.
Yeah, my question is about the normalization of the train test and then norming the test set to the train set. How do you actually code that?
Yes, so this is something we haven't touched yet, and we actually won't touch until a little bit later.
Okay.
We might introduce, maybe we can do this earlier on as a study group, but something called pipelines and are really useful. And the idea here is you have a pipeline kind of put together, and it represents essentially say, do these steps. And basically you can pass this pipeline into your train set or your test set or whatever you're doing. And what's nice is that sklearn actually builds these pipelines. Like you can essentially, if you use just sklearn, you can actually, hey, go ahead and use this, you know, normalization, this fitting, this pre-processing step, and then into like your model. And what's really cool too, this is where object-oriented programming can be really useful. You can define your own, like, let's say you're something like, well, I need to do a very special thing here that sklearn doesn't have, like a normalization. I need to do it in a very way, like talk about, like, you know, maybe the way it like pre-processes the data. You can define it with an object-oriented programming class, like that's built into sklearn, and pass it into your pipeline. So, and then all you have to do essentially is export your pipeline to production, and the production team can basically take that and use that pipeline for all the incoming data that you've never seen, essentially actually putting it in like use. So yeah.
Okay, cool.
Cool. Yeah, but maybe we'll talk about that earlier on. I think we don't talk about it technically in the curriculum until much later, but I think it might be an important aspect to kind of check out.
Okay.
All right, good questions, guys. All right, cool. So going back a little bit to our little example, we have our test set, right? So we're going to see how well it does. So we have our evaluate the model, our training set. So we can kind of see how well it performs on the training set, which hopefully does pretty decently, right? Might not be perfect. You can see here 117 out of 117 were true, 3 were falsely predicted. So we didn't say exactly how they're false, but like it was, no wait, I have this right? Oh yeah, okay, sorry. This true and false kind of threw off because of the positive. Basically, these were correctly identified, these were incorrectly identified. Okay, and we can see a percentage. We can see the percentage is 97.5. Not bad, right? So pretty good. Now we want to check out the testing set, which I think is about 30 points. So we'll see what other residuals are. We can see we got 28 were true and 2 were false. Okay, pretty good. And we can see percent-wise 93, which again makes sense. We didn't expect to do as well as training. Some subtlety kind of comes in here, which is kind of leads us into our next part with the evaluation is we see like this, like 3 are false, or like these 2 are false. We didn't really say like they were just false in the sense that they were not identified correctly. But we didn't say like, was it a false one that we like, let's say our target is 1, right? And our positive is 1, 0 is false, right? Did we misidentify our false? Did we get a false negative, or did we get a false positive? Accuracy by itself doesn't actually tell us that. And that's where we go into deeper evaluation metrics, because it's more than just saying how far away is it, like linear regression. It's like there's a couple ways you can be wrong. You can either have a false positive or a false negative. And that's where evaluation metric will come in. Okay, cool. Sound good so far? Any questions on Scone?